I want you to do something for a second. Um, just look around the room you're sitting in right now.
Yeah, take a really good look at the space between you and the wall.
Right, or like between you and your screen.
Mm-hmm.
Because it looks entirely empty,
Yeah.
Up until I sat down with the sources for today's deep dive, I always just thought of that space as, well, just a void that we happen to walk through.
Like it's the default setting of the universe or something.
Exactly. But the central premise we are exploring today, it completely shatters that illusion. Because right now, you are sitting at the bottom of an ocean. Not an ocean of water, obviously, but a literal physical ocean of air.
And we are so habituated to its presence, right, that we're entirely blind to it. We treat the atmosphere as an absence of stuff.
Yeah.
But it is a tangible physical substance. I mean, it has mass, it has structure, and crucially, it has weight.
Which is wild to think about.
It really is. Like, if you were to take a standard-sized living room and weigh just the air inside of it, you would find it weighs about 100 pounds.
Okay, wait, hold on. If there's 100 pounds of invisible stuff just sitting in my living room and, miles of this stuff stacked on top of my head, why don't I feel heavy?
Right, that's the natural question.
I mean, I can wave my hand in front of my face and feel almost zero resistance. So if I'm at the bottom of an ocean of weight, why aren't we all just being crushed?
Well, the simple answer is internal pressure.
Okay.
The human body evolved at the very bottom of this specific ocean. So the fluids and gases inside your body are actually pushing outward with the exact same force that the atmosphere is pushing inward.
Oh, wow.
Yeah, it's this perfect equilibrium. But that immense weight is always there, pressing down on every square inch of you at roughly 14.7 pounds per square inch.
That is almost claustrophobic when you actually stop to visualize it.
It really changes your perspective.
It does. I've spent my whole life treating the air like this passive backdrop. So the goal for this deep dive is to stop taking this invisible ocean for granted, to understand what it actually is, how it's built, and how it literally colors our world.
I love that.
So let's start with the recipe. What are we actually swimming in? Because honestly, if you'd asked me yesterday, I would have confidently said we are swimming in oxygen.
And you would be joining a vast majority of people who think the exact same thing.
It just makes sense, right?
It does, because we require oxygen to survive, so our brains just assume that's the primary ingredient of the air around us. But oxygen only makes up about 21% of the atmosphere.
Which leaves a massive chunk unaccounted for.
Right. Almost all the rest, about 78%, is actually nitrogen.
70%.
Yep. And nitrogen is largely defined by what it doesn't do.
What do you mean?
Well, it's highly unreactive. It mostly just sits there diluting the oxygen. And honestly, we should be very thankful for that dilution.
Why is that?
If our atmosphere was purely oxygen, the world would be incredibly flammable. Like a single spark would ignite massive, uncontrollable firestorms everywhere.
Oh, wow. Okay, so the air is essentially a giant smoothie, and the nitrogen is the ice.
The ice.
Yeah, like it's the filler giving the drink volume so the active ingredients aren't so intense that they burn the house down.
That is actually a highly accurate way to look at it. The nitrogen provides the safe bulk. So you've got 78% nitrogen, 21% oxygen.
Right.
That leaves just about 1% of the atmosphere. And this tiny remaining fraction is made up of what scientists call trace gases.
Trace gases. Now, my assumption is that if something is a trace amount, it's basically a rounding error.
Yeah.
Like it shouldn't matter that much.
It sounds like it shouldn't matter, yeah. But
Yeah.
that 1% dictates the climate of the entire planet.
Really?
Absolutely. This fraction includes a gas called argon, along with water vapor and carbon dioxide. And carbon dioxide is the perfect example of something punching far above its weight class. Well, it makes up just a microscopic fraction of the air, about 0.04%. Yet it is the primary thermostat for Earth.
Okay, I need to push back on that for a second because the math feels completely counterintuitive.
Yeah.
How can 0.04% of anything control the temperature of an entire planet?
It's crazy, right? It all comes down to molecular structure.
Okay.
Carbon dioxide molecules have a very specific physical property. When visible light from the sun hits the Earth, it passes right through the carbon dioxide. It doesn't interact with it at all.
It just goes right past.
Exactly. The sunlight warms the surface of the Earth, but when the Earth tries to radiate that heat back out into space, the heat takes a different form. It becomes infrared radiation.
So the energy actually changes shape after it hits the ground.
Yes, exactly. And carbon dioxide molecules are highly reactive to infrared radiation.
Oh, I see.
So when that heat tries to leave, The CO2 molecules absorb it. They physically vibrate, and in doing so, they radiate that heat back down toward the surface.
Wow.
Even at microscopic concentrations, there are enough of these molecules forming this invisible thermal blanket that keeps the heat from escaping. It's the reason Earth isn't just a frozen, lifeless rock.
It's basically a one-way mirror for heat. Like the sun's energy can check in, but a lot of it can't check out.
A one-way mirror is a great visual. And because that trace amount is so incredibly powerful, even tiny adjustments to that 0.04% have massive, cascading planetary consequences.
It's staggering to realize our entire existence relies on such a delicate chemical balance.
It really is.
So we have this mix, right? The nitrogen ice, the oxygen flavor, and the highly potent trace gases. But the sheer mass of all this gas settling onto the planet means it isn't just swirling around randomly.
Right. It's highly structured.
Yeah, it settles into highly organized layers. The source text described it like a layer cake, where each level has a completely different physical reality.
Yeah, the layer cake analogy is perfect. We start at the very bottom layer, the one we are physically sitting in right now. It's called the troposphere.
The troposphere.
Right. Every mountain, every forest, every city exists here. And crucially, it is where all of our weather happens.
All of it.
All of it. The clouds, the hurricanes, the gentle spring rain that is all just the troposphere churning and boiling.
You know, the scale of this layer gave me vertigo when I read it. Because when you stand outside and look up at a massive, towering thundercloud,
Yeah,
it feels like the sky goes up forever.
it does feel endless.
But the troposphere is shockingly thin. It's only about 10 to 15 kilometers thick.
It totally shatters the illusion of an endless sky.
It really does.
Yeah.
The text used an analogy I cannot stop thinking about. If I could get into my car and somehow drive straight up into the sky at highway speeds, my normal daily commute would literally take me out of the weather entirely.
Yeah, you'd just punch right through.
Like 10 or 15 minutes of driving and I'd be through the roof of the troposphere. It just makes this environment we live in feel incredibly small.
It really is a thin bubble, but if you keep driving your imaginary car upward, you cross a boundary into the stratosphere.
Okay, the stratosphere.
And because it sits above the churning heat of the Earth's surface, it is incredibly stable. There's almost no vertical movement of air, which means there are no storms, no clouds, no weather.
Which totally explains why commercial airliners climb to 35,000 feet.
Exactly.
They are literally climbing out of the troposphere to skim along the bottom of the stratosphere just to avoid the weather.
Yeah, they want that smooth, stable air, but the stratosphere does something much more vital for us than just provide a smooth flight. It contains the ozone layer.
Right, the famous ozone layer.
Ozone is a molecule made of 3 oxygen atoms bound together, and it acts as the Earth's biological shield.
We throw that term around constantly, usually in the context of it being damaged,
Yeah.
But how does an invisible gas actually act as a shield against something as powerful as solar radiation?
It's actually a process of sacrifice.
Sacrifice.
Yeah. When high-energy ultraviolet radiation from the sun slams into the stratosphere, it hits these ozone molecules. The ozone absorbs that immense energy, and the molecule is physically shattered apart by the impact.
Wow, so it takes the bullet for us.
It literally does. And then, through natural chemical reactions, those shattered pieces eventually recombine back into a new ozone molecule, ready to take another hit.
That is incredible.
It's a continuous cycle. Without that invisible layer of molecules constantly shattering and reforming, the surface of the Earth would be sterilized by UV radiation.
Okay, so the stratosphere is handling the energy and the radiation from space. But space isn't just radiation.
No, definitely not.
It's full of actual physical garbage, right?
Right.
Rocks, dust, ice. Does the atmosphere do anything to protect us from the physical stuff falling in our heads?
That brings us to the next layer up, the mesosphere.
The mesosphere.
This is a much colder, thinner layer of gas, but it acts as a cosmic incinerator. When the space debris, meteors fall toward Earth, they're traveling at tens of thousands of miles an hour.
Right.
When they hit the mesosphere, they vaporize.
See, I struggle with the physics here. If the air in the mesosphere is incredibly thin, which it must be, since it's so high up, how is there enough friction to completely vaporize a solid rock?
It's a common misconception that it's just friction.
Oh, it isn't.
No, it is primarily something called ram pressure.
Ram pressure.
Because the meteor is moving at such an extreme velocity, the thin air in front of it simply cannot get out of the way fast enough, so the air is violently compressed. And in physics, when you rapidly compress a gas, it heats up.
So the meteor isn't rubbing against the air, it's squishing the air into a superheated plasma wall.
Exactly that. The air in front of the meteor reaches thousands of degrees, and that intense heat melts and vaporizes the rock.
That is wild.
So those beautiful romantic shooting stars you see at night, that is just ram pressure in the mesosphere, destroying a rock before it can hit the ground.
The atmosphere is doing an unbelievable amount of heavy lifting. We have the weather layer, the radiation shield, and the rock incinerator.
And one final highly active layer above that, the thermosphere.
Thermosphere.
The gas here is so incredibly sparse that you would consider it a vacuum in any laboratory on Earth. But it is here that the solar wind interacts with the scattered molecules to create the auroras, the northern and southern lights.
Oh, beautiful.
And if you look up and see the International Space Station moving across the night sky, it is orbiting within the thermosphere.
Wait, hold on. If the space station's in the thermosphere, and the thermosphere is part of the atmosphere, is the space station actually in space? Like, where is the boundary line?
Well, there is no solid border. The atmosphere doesn't just hit a brick wall and turn into the vacuum of space.
It doesn't.
No, it just slowly, gradually fades away. The molecules get further and further apart until they are essentially gone. So the space station is in space, but there are still enough stray air molecules up there that they create microscopic drag on the station, slowly pulling it down.
Oh, I had no idea.
Yeah, that's why it has to occasionally fire its thrusters to boost itself back up.
Which brings up a massive question for me. If there is no lid on the atmosphere, and it just fades into an empty vacuum, why doesn't it all just float away?
We circle right back to where we started, weight and gravity. Because air is a physical substance with mass, the Earth's gravity pulls on it, anchoring it to the planet.
So it sounds like stacking 100 fluffy pillows on top of each other.
Oh, I like that.
Yeah, like the pillow at the very bottom of the pile where we're sitting is going to be squished completely flat by the sheer weight of the 99 pillows on top of it.
Right.
So it's dense and compacted, but as you climb up the pile, there's less weight pressing down. The pillows in the middle are fluffier,
Yeah.
and the one at the very top is completely unsquished, just barely resting there before floating off.
That is the perfect way to visualize atmospheric density. The weight of all those upper layers squeezes the molecules at sea level tightly together.
Yeah.
And as you move higher, climbing up your pile of pillows, the pressure drops, the molecules spread out, and the air thins.
Which completely explains why high-altitude mountain climbers are always gasping for breath. The recipe of the air hasn't changed. It's still 21% oxygen, but the air is so fluffy and spread out that every physical breath pulls in drastically fewer oxygen molecules.
Exactly. Their lungs are trying to operate in an environment they aren't calibrated for. The pressure simply isn't there to pack the oxygen densely into their bloodstream.
So down here at the bottom of the pillow pile, we have this dense, squeezed obstacle course of nitrogen and oxygen molecules.
Right.
What happens when something tries to pass through this obstacle course? Like sunlight. Because this brings us to the physics of color and the ultimate childhood question, why is the sky blue?
It is the question every parent dreads, but the physics behind it are incredibly elegant.
I can't wait.
First, we have to look at the sunlight itself. The light pouring out of the sun looks white to us, but white light is actually a bundle of all the colors of the rainbow traveling together.
We see that when light hits a prism, right, or a raindrop and fractures into a rainbow.
Yes, and light travels in waves. The crucial detail here is that each of those colors has a different physical wavelength.
Okay.
Red light travels in long, sweeping, lazy waves. Blue light travels in much shorter, choppier, tighter waves.
So we have this bundle of different-sized waves crashing into the top of the atmosphere.
And as they push down into that dense lower layer, they start hitting things. They hit those tightly packed nitrogen and oxygen molecules.
Right, the obstacle course.
When light hits an object in the air, a process called scattering occurs. The light bounces off the molecule and ricochets in a new direction.
But the molecules don't treat all the colors equally.
Not at all. Think of the light waves like water waves hitting a small rock in the ocean.
Okay.
A massive, long ocean swell, which represents our red light, will just wash right over the rock undisturbed. It pushes straight through.
Got it.
But tiny, choppy ripples, our blue light, will hit the rock and splash everywhere. Because the blue wavelengths are so short, they constantly crash into the air molecules. The blue light bounces from molecule to molecule, scattering wildly across the entire sky.
It's like a massive game of pinball. The blue light is the ball constantly hitting the bumpers, lighting up the entire board, while the red light is heavy enough to just drop straight down the middle without touching the sides.
A planetary game of pinball, yes. When you look up at the sky during the day, you aren't seeing an empty blue void. You are physically seeing that scattered blue light ricocheting around the dense lower layers of our air.
I feel a profound sense of satisfaction finally understanding the mechanics of that.
It's pretty cool.
But if the sky is a blue pinball machine, what happens at sunset? Why does the sky suddenly turn into this dramatic painting of fiery reds, oranges, and purples?
The beauty of this is that the exact same physics explains both. Yeah, nothing about the air changes. What changes is the geometry of the light's path. At noon, the sun is directly overhead. The light takes a short, straight shot down through the atmosphere to reach your eyes.
So it only has to travel through that 10-mile slice of the troposphere.
Right. But as the sun lowers toward the horizon, the angle changes. The light is no longer coming straight down. It is coming at us from a severe sideways angle.
Okay, I see where this is going.
That means the light has to push through a much thicker, longer slice of the atmosphere to reach you.
The pinball board just got 10 times longer.
And along that much longer journey, the blue light is still hitting the bumpers. It's still scattering wildly. But because the path is so long, the blue light scatters so much that it is completely exhausted.
Oh, wow.
It scatters away in other directions before it can ever reach your eyes.
The blue is entirely filtered out.
Exactly, leaving only the longer wavelengths, the reds and the oranges.
The long ocean swells.
Right, the swells that wash over the obstacles. They are the only light strong enough to push straight through that thick horizontal slice of atmosphere. A beautiful red sunset is literally just the leftover light, the survivors of a long journey through the air.
Leftover light. That is an incredibly poetic way to view it. The same light, the same gas, just a different angle, causing a completely different visual experience.
It's amazing.
It really drives home just how active and dynamic the air is. It's performing complex physics every single second.
Yeah.
But, it feels like this environment is almost too perfectly tailored for us. The sources point out that this wasn't the original recipe, was it?
No, not at all. The early Earth would have been a toxic, unrecognizable nightmare. There was no breathable atmosphere, no protective ozone, no blue skies.
What was it then?
The atmosphere was mostly carbon dioxide, methane, and ammonia, belched out by early volcanoes. It would have choked us in seconds.
So how do we get from a volcanic nightmare to the perfectly balanced, oxygen-rich environment we have today?
We owe our existence to biology.
Biology.
Yeah. Billions of years ago, the very first tiny living things, microbes in the early oceans, developed the ability to photosynthesize. They took in sunlight and the abundant carbon dioxide, and as a waste product, they released oxygen.
A gas that didn't even exist in the atmosphere before them.
Not in any meaningful quantity, no.
Oh.
Generation after generation, for billions of years, these microscopic organisms quietly pumped oxygen into the sky. They essentially terraformed the planet. Life itself manufactured the breathable atmosphere.
I'm having a bit of a crisis realizing this.
There's lots to take in.
We constantly treat the atmosphere like this passive backdrop that just happened to be here waiting for us. But it is an active, hardworking life support machine built by biology.
That's exactly what it is.
Let's just look at its resume for a second, because the list of things it does is staggering. The mesosphere acts as a cosmic incinerator, vaporizing space debris.
And the stratosphere houses the ozone layer, taking the bullet from the sun's radiation so the surface doesn't get sterilized.
The trace gases trap just enough heat to keep the oceans liquid and the planet habitable.
And the troposphere acts as a global transit system for fresh water, ferrying water vapor around the globe and dropping it as rain to water our crops and fill our rivers.
It's insane.
If any single one of those systems fails, the planet quickly becomes hostile to life.
It is a perfectly calibrated machine.
It really is. And as we step back to look at the whole picture, there's a final sense of scale that the sources provide, which is vital to understand.
Okay, what's that?
Because when you stand in a field and look up at a clear blue sky, the atmosphere feels limitless, right? It feels so vast that nothing we do down here could possibly impact it.
Right.
But relative to the size of the planet, it is shockingly thin.
How thin are we actually talking?
Imagine you could shrink the entire Earth down until it was the exact size of an apple and you're holding it in the palm of your hand.
Okay, I have the apple.
If Earth were that apple, the entire atmosphere, the layer holding all our weather, all our breathable oxygen, every cloud, bird, and commercial airplane would be thinner than the skin of the apple.
Thinner than the skin of an apple.
Astronauts talk about this phenomenon constantly. It's called the overview effect.
The overview effect.
Yeah. When they arrive at the space station and look back at Earth, they expect to see an endless sky. Instead, they see this delicate, glowing, incredibly thin sliver hugging the edge of a massive rock against the black void of space.
That sounds beautiful.
They frequently remark on how fragile it looks and how seeing that thin blue skin completely rewires their brain regarding how we treat it.
It's terrifying, but it also instills a deep sense of awe. I want to leave you, the listener, with a final thought to mull over today as you go about your routine.
Yeah.
Think about that apple skin. Every breath ever taken by every human, every animal, every dinosaur, every living thing in the history of this planet has happened inside that microscopic, fragile, glowing sliver of gas.
It's humbling.
It really is. And if our entire existence relies on a layer thinner than an apple's skin, how much more carefully should we be thinking about altering that tiny 1% of trace gases that keeps the whole system balanced?
It is a question that requires our full attention, absolutely.
Thank you for joining us on this deep dive. The next time you step outside, I challenge you to really look up. Look at the scattered blue light ricocheting around the pinball machine. Feel the pressure of the ocean stacking up above you. Stop taking the void for granted and really see the ocean you are walking around in. We'll catch you next time.